As you can see from the title of this video, this tutorial is about electron dot notation. Electron dot notation is the last of the three types of ways we will try to describe the location of electrons around the nucleus of the atom. What makes electron dot notation different than other notations that we've done? In some ways it's much simpler, but in other ways it is much more useful. Right? It tells us less about the atom in total, but it tells us a great deal more about atoms' reactivity, which is a large portion of chemistry. It's how two atoms come together and why they behave the way they do once they collide with each other. How electron dot notation works is it looks at the highest energy level electrons. We refer to the highest energy level electrons as valence electrons. So if I refer to a valence electron, what I am talking about is the electrons that are farthest away from the nucleus, that are in the highest energy level, right? Because remember, as you move farther and farther from the nucleus, further and further from the nucleus, you get higher in energy. Here is how electron dot notation works. You write the symbol, nuclear symbol, like sodium's is Na, of the element, and then you put a dot for every valence electron that it has. To be able to determine the valence electrons, you have to be able to write an electron configuration. So, if you look at something like fluorine, fluorine has 9 electrons. If I were to write an electron config for this, it would be 1s2, 2s2, 2p, 5. And there are my 9. If I were to draw a picture of this, I would have my nucleus. In my first energy level, I would have 2 electrons in an s orbital. Right? So they would be in a sphere area around the nucleus. In my second energy level, I would have 2 electrons in an s orbital and 5 in a p. So if you were looking, if I want to look at valence electrons, I have to look at the highest level. Now, the good news is you don't have to draw a picture to figure this out. The highest level is indicated by whichever one have the largest quantum number at the beginning. Right? 2 is the highest energy level. To figure out the total number, I would add up the superscripts. So this atom has 1, 2, 3, 4, 5, 6, 7 valence electrons. So I would take the symbol for fluorine, F, and I would put 7 dots around it. I start by putting 1 dot on each side of the symbol and then pairing them up. So my 7 would look like this. 1, 2, 3, 4, 5, 6, 7. Now, it doesn't matter where your singly unpaired one is. I always treat these like sides of a house. Top, right, left, bottom. Right? If the single electron were on the top, the right, or the bottom, that would also be fine. You need 3 pairs and 1 single even. And this has 7 valence electrons. If we were to look at something a little different, like lithium, Li has 3 electrons. Its configuration, 1s2, 2s1. So if I'm doing a dot structure, all I care about is the highest energy level in front. It's a 2. There's only 1 2, and there's 1 electron in it. So lithium would be Li with a dot somewhere on the side. Be careful as you go through and do this, because dots on I's can sometimes stray and look like electrons. If we were to look at a third one, we could do something like sulfur. Sulfur has 16 valence electrons, and with its 16 valence electrons, 16 total electrons, its configuration would be 1s2, 2s2, 2p6 gets us to 10, 3s2 is 12, 3p4. So looking at this, The highest level I see is 3. With that being said, there's 2 in this third level, 4 in this one, so there are 6 valence. So I would have sulfur S with 6 dots. 1, 2, 3, 4, 1 on each side, 5, 6, pair them up. That would be the electron dot notation for sulfur. Let's take a look at one more, like scandium. SC. Scandium gets 21 electrons. With it having 21 electrons, its configuration would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 2, 4, 10, 12, 18, 20, 3d1. I picked this one specifically to show you you cannot just zero in on the last config. This doesn't have 5, it has 7, because the last 2 were a 2. This one does match. It has a 1 in the last config, it's the highest level, it gets 1. This one here, it's not 4 dots, there's 2 3s, it's 6 dots. This one, even more so, you have to find the highest level, and the largest number here is not at the end. 4 is the highest orbital notation number that we're looking at, the quantum number. So, all I care about is the electrons in the 4, and I don't worry about these 3s and 2s and 1s, which means scandium, SC, simply gets 2 dots. And all of these other electrons that follow go into lower subshells that are not the highest energy level. So the key to this is finding your highest energy levels, looking at their superscripts, adding them up, and then adding the appropriate dots, remembering that what you're really doing is focusing on the electrons that are farthest away from the nucleus. Hope this clears up any problems that you might be having. If not, please come in for some additional help.